In Chapter 19, we're going to continue our study of the atmosphere and take a look at weather patterns and then study some of the severe weather patterns, thunderstorms, tornadoes, and hurricanes. So, in order to understand where our day to day weather comes from, we first have to look at air masses. So, air masses are responsible for our weather patterns. And what we're going to look at is the movement of these air masses. So, air masses are very large bodies of air, 1,000 miles or more across, several kilometers thick. And when we look at these air masses, they're characterized by a similarity in the temperature and the amount of moisture in a given altitude. So the air mass is going to develop and then move out of that area, bringing those temperature and moisture content with it. And so this is then going to affect a large portion of the continent and give us our day to day weather. So here is an example of an air mass. So we have this cold, dry air mass originating up in, pretty much close to the Arctic Circle, way up in northern Canada. And the beginning temperature you see there is negative 46 degrees Celsius. So that's the starting temperature. So as it moves down through Canada and through the United States, it's warming up some because it does interact with the air that's already in place. But you see, if we look at Dallas, negative 9 degrees Celsius, 16 degrees Fahrenheit. So this air mass is bringing cold air with it. Okay. It brings some of the coldest weather of the winter to places that are in its path. And this is what happened last February when it stayed cold for so many days in a row. We had a polar air mass that came down, bringing all of that air with it. Air masses extend over large areas. There will be a little bit of temperature variation and humidity difference from place to place, but we're looking at the overall pattern. It can take several days for an air mass to move through an area and be modified. And so that region that's under the influence of that air mass will experience fairly constant weather, which is called air mass weather. Air mass and looking at these air masses and where they develop and how they move is important because it allows us to be able to study atmospheric disturbances. So the source region is the area where the air mass begins, or its source. So it's going to share those properties of temperature and moisture. So we classify them based on their region and the nature of the surface. So we've got polar, tropical, continental, and maritime. So polar, these are going to come from high latitudes. They're going to be very cold. Tropical come from the lower latitudes. These are warm. Continental air masses form over land, and most of the time they're going to be dry. And then maritime form over water, so they're going to be carrying more moisture so they can bring in the humidity. So if we look at the United States, and we are really going to focus on the United States, Canada and Mexico here in this section, because we're looking at our mid-latitude weather. So we've got the continental Arctic, continental polar, so we have those very cold coming from the north. Then you see the maritime polar and maritime tropical. So the maritime polar would come south. The maritime tropical would be formed over land and come up north. And then we have a really small continental tropical air mass as well. So if we look at the weather that's associated with these air masses, so if we focus on North America east of the Rockies, the continental polar and the maritime tropical air masses are going to be most relevant here. The continental polar in the winter brings cold, dry air. In the summer, if we get a continental polar air mass, it's going to bring some relief from the hot temperatures. As these air masses cross the Great Lakes, they can pick up moisture from the lakes and initiate what is called lake effect snow. And this is something that you may have heard on the weather when they talk about the areas of like Erie, Pennsylvania, Buffalo, New York, in those areas that are up there by the Great Lakes, they get massive amounts of lake effect snows in the wintertime. So now we're going to watch a SmartFigure video that is going to look at these lake effect snows.
Hi there, this is Callan Bentley. Welcome back for another SmartFigure. After watching this video, you're going to have a better sense of how lake effect snow forms. This is what we want to talk about here. If you take a look at this picture, this is a pretty extraordinary image. You're looking at the Great Lakes region. So Lake Superior is up here in the upper part of the image, something like that. And then we've got Lake Michigan coming down here, something like that. You can see that their western and northern shorelines are relatively cloud-free. And then as you get out over the middle of the lake, thin clouds begin to form, and they're aligned in rows that are basically parallel to the wind direction. So the winds must be blowing basically like this across these lakes. And then you can see they get thicker and thicker and thicker and whiter. And then as you get over to the southern and eastern shores, you can see that those shores are pretty white. Of course, there's a lot of white on this map, but this is what lake effect snow is all about. We learned the names for these different air masses, right? And one of those air masses is going to be really relevant for lake effect snows, and that's the continental polar air mass. So in the winter, this is the cold, dry air that moves off of the Arctic portion of the North American continent, and it crosses the Great Lakes. As it does that, it interacts with the lakes. The lakes are relatively warm, and of course they've got lots of moisture. A lot of that heat energy and that moisture is transferred to the overlying air mass, which then basically becomes unstable by the time it gets over to the far shore. And as a result, it ends up dumping a bunch of snow once it gets over there. And so you can see that there's sort of this almost like a little visual echo of the lakes that's offset towards the east of each of those lakes. So that's lake effect snow. And it can be really, really thick. They get tremendous quantities of snow in these regions, in some places in excess of 130 inches a year. So we're talking on the order of like 10 feet a year, 3.5 meters deep of snow. So that can be a really big load. So when you look down from space at this amazing scene, realize that the people who are living right here and right here are totally getting slammed with snow. Now let's test your knowledge. This is a hypothetical continent. It's going to be in the southern hemisphere. So rather than the winds tracking from west to east across the continent as they do in the northern hemisphere, the prevailing winds are going to be tracking from the east towards the west. Likewise, something that'll be a little bit different because it's in the southern hemisphere is if you have a continental polar air mass, it's going to be coming from the south towards the north. Now, make a prediction about where the snow is going to end up being relative to these lakes that are located in the middle of this hypothetical continent. Well, you can imagine that that air mass moving north is going to basically get pushed along by the prevailing winds, so it's going to take a path over those lakes that's going to look something like this. And then that's going to result in snow accumulating basically on the downwind side of the lakes, almost like a little shadow of those lakes that's located to the north and the west of those lakes.
Now, if we look west of the Rocky Mountains, and I realize I made an error on this PowerPoint, if we look west of the Rocky Mountains, so the area where we are located, we are also influenced by maritime tropical air masses, but these are coming from the Gulf of Mexico and the Atlantic Ocean, bringing very warm, moist, and unstable air. We can also get influenced by the continental tropical air mass, but this one is a little bit smaller and doesn't tend to move as much as the others. So we're really looking at the Southwest, like West Texas, Arizona, New Mexico, and then Mexico south of that. This is very hot, very dry air, and that's what can be in place in those areas where they have very little humidity. The maritime polar can also influence the area east of the Rocky Mountains, especially as we get up into the New England region. And this creates what we call a nor'easter. There is an image in your book on page 581 of this classic nor'easter. It kind of looks almost like a hurricane, but this is due to that a maritime polar and a continental polar air mass. So when two air masses of different densities clash, this is called a front. And this is something that we really see a lot in the middle latitude, and that's why we're kind of focusing on the United States here. When air masses, particularly if we have a colder air mass and a warmer air mass, collide, and they create this boundary we call a front or a frontal boundary. Usually, it's a cold and a warm air mass, but it could be air masses of similar temperatures or similar moisture, similar humidity. The air mass, generally speaking, okay, the air mass on one side of the front is going to move faster than the air mass on the other side. And so one is basically going to advance. So typically what happens is the air masses are not going to mix. They're going to retain their identities. So when they collide, especially if we're talking about a cold air mass and a warm air mass, the warmer air is less dense. And so it's forced aloft, and the cooler air acts kind of like a wedge underneath it. This is called overrunning when you have this condition. So now we're going to look at the different types of fronts that we can have. We have warm fronts, cold fronts, stationary fronts, and occluded fronts. So I'm going to show two SmartFigure videos, one on warm fronts, one on cold fronts, and then I'm going to come back and discuss the other two types that we have.
When air masses of different temperatures meet, they do not mix readily. Instead, an abrupt boundary, known as a front, forms. Warm fronts. Where a warm air mass advances into an area of cooler air, a warm front develops. As the warm air mass advances, it slowly pushes the denser cold air mass, but most of the warm air simply rises over the colder air. As air rises along the warm front, it undergoes adiabatic cooling. This cooling typically leads to cloud formation and drizzly precipitation along a warm front. Because the lifting along a warm front is usually quite gradual, cloud development is often more widespread and precipitation less intense than that associated with the more abrupt lifting of air along a cold front.
So what you notice here is the warm front, the warm air colliding with the cool air, and the warm front you see is designated by this red line with these little semicircles. And the semicircles are pointed in the direction that the air is moving. Okay, so there you see you've got your nimbostratus, so your kind of your rain clouds, and then your stratus and altostratus, cirrostratus clouds. So what happens typically in a warm front is that we get some precipitation. Often in the form of snow in the wintertime, in late fall and early spring. It can be snow, sleet, freezing rain, really depending on how warm or cool that air mass is. Thunderstorms typically in the spring or fall.
When air masses of different temperatures meet, they do not mix readily. Instead, an abrupt boundary known as a front forms. Cold fronts. Where a cold air mass advances into an area of warmer air, a cold front develops. As the cold air mass advances, notice that it displaces the lighter warm air upward. As air rises along the cold front, it undergoes adiabatic cooling. This cooling typically leads to cloud formation and precipitation along and just behind a cold front.
So here you can see with a cold front, the cold air is advancing and the warm air is going over the top of it. You'll notice a cold front is represented by a blue line with blue triangles, again pointing in the direction that the cold air is moving. And this time we get the formation of our cumulonimbus clouds, or our thunder clouds, thunderstorm clouds. When the cold front approaches, you can typically see the towering clouds, because remember, cumulonimbus clouds are very towering. They get stacked up. And there may be a dark line of clouds that you can see as the storm approaches. When the warm air is lifted, it typically occurs rapidly, and so that latent heat that's released when the water vapor condenses increases the buoyancy of the air. So this often is associated with heavy downpours, vigorous wind gusts. The cold front is going to produce the same amount of lifting as the warm front, but over a shorter distance. So the intensity of the precipitation is greater. We also tend to see more violent weather with cold fronts. Clearing usually begins soon after it passes, so typically don't last as long as we see with warm fronts moving in. So now we'll take a look at stationary fronts and occluded fronts. So in a stationary front, the flow of the air is almost parallel to the line of the front. So the surface position of the front doesn't move. On the weather map, which you'll see here, well, I thought so. Oops. I'll bring that up a little bit later. I thought I had a weather map. Maybe it's on. There it is. It's on page 585 in your book is where it is. So the stationary front you'll see has both triangles and the little semicircles. The triangles point towards the warmer air and the semicircles point towards the cooler air. In an occluded front, an active cold front is going to overtake the warm front, and as the cold air and warm air meet, as that warm air wedges on top of it, a new front is going to emerge between the advancing cold air and the cooler air. With an occluded front, it's kind of hard to predict what type of weather is going to result because it's very complex. Most precipitation is going to be associated with the warm air being pushed on top of the cold air, but the occluded front can produce precipitation on its own. In an occluded front, it's shown in purple with the triangles and the semicircles both on the same side. So here's what happens in an occluded front. So you've got this kind of advancing area of cold air here, and you've got warm air, and then you've got some cooler air. So the cold air is going to hit the warm air. That's going to produce basically the effects of a cold front where you get this cumulonimbus cloud. However, the surface cold front that's coming in here is moving faster than the warm front. And as it overtakes it, it produces this occluded front. And the cold air now is going to lift the warm air to displace the cool air that's on the other side. So essentially what happens is you get a cold front overtaking a warm front, because that's kind of what you've got. Your cold front coming in here, you've already got a warm front in place here, and the cold front just overtakes the warm front to form an occluded front. Now, when we look at these air masses, we look at fronts. That's kind of the basic elements of weather. So now we're going to look at how all of this comes together and all of it interacts to produce our weather. And this occurs from what we refer to as mid-latitude or middle latitude cyclones. We talked in the last chapter about cyclones and anticyclones. And remember that cyclones are essentially areas of low pressure. And they generally travel from west to east, last a few days to a week, and typically form along a front where air masses are moving parallel to the front, but in opposite directions. So here's that weather map, okay? And so here's kind of showing our warm front over here, our cold front here. Here's a stationary front over here, and then here's an occluded front over here. So what happens is you get this low pressure system that's set up as the winds start to rotate around it. So now we'll watch another SmartFigure video about the formation of these mid-latitude cyclones.
Hi there, this is Callan Bentley. Welcome back for another SmartFigure. In this video, we're going to take a look at mid-latitude cyclones, which are the dominant weather systems that affect North America. Here's a weather map taking a look at a mid-latitude cyclone. Notice that it's this low pressure system that's indicated by the letter L, and it occurs where several air masses meet up, a continental polar air mass, a marine polar air mass, and then a marine tropical air mass. You'll notice that these air masses are divided by fronts, cold fronts and warm fronts, and in some cases an occluded front or a stationary front. In 3 dimensions, this low pressure system that we were just looking at looks something like this. You can see here that the cyclonic flow is basically an inward flow. So air is moving in towards this low pressure system from surrounding higher pressure areas. And you can have a neighboring high pressure area where air is moving out because that's a descending mass of air. So the low pressure system ultimately is an ascending mass of air. And you can see basically this very large scale sort of spool shaped spiral that's moving up towards the jet stream up at elevation. Here's another look at a mid-latitude cyclone. You can see here that we have the clouds illustrated, and you can see that these clouds sort of have an overall comma-like shape. You can compare that, say, to this satellite image where you have your low pressure system approximately here, and then you've got this sort of cold front here and a warm front kind of trailing in, something like that. So what we want to do now is we want to take a cross-section. Actually, let's take 2 cross-sections through this system so we can get a sense of what's happening where. The first cross-section will be this line from A to E. Notice that there are several points along that line. So we've got A over here in the Atlantic Ocean, E here in East Texas, and then we've got points D, C, and B along that line. Let's see what it looks like if we were to slice open this system along that line. So here's A over on the far right. E and East Texas is over there in the left. And we can see that we've got 3 air masses here, a cool air mass, a warm air mass, and a cold air mass. And this zone right here between B and C is where we have a warm front. And so that warm front is moving from position C towards position B, and it's basically shoving that warm air up. So you can see as that warm air rises, you get cirrus and cirrostratus, altostratus, and nimbostratus clouds, and you get moderate precipitation there. Meanwhile, over here at position D, that's where the cold front is moving in. And that cold front is wedging that warm air up. That warm air is rising, carrying with it its load of moisture. As it rises in the atmosphere, it is forced to cool down, and it basically drops its load of moisture as precipitation. So you end up getting cumulonimbus clouds, and just in front of them, cumulus clouds. And that's where you have really heavy precipitation right there at the cold front. Okay, so that's what we see going on in this area here. Now let's see what's happening, say, up further to the north. Let's draw a cross section along this line from point F to point G. That cross section would look something like this. So here's point F, over here on the left is point G, and you can see that basically we have one continuous cold air mass there, but the cold air extends to a higher elevation on the fringes, like basically at points F and G, and closer to the low pressure system itself. You end up seeing that the warm air dips down to a lower level, and you end up seeing nimbostratus clouds at that location, and you end up having moderate precipitation there as well. This would be that area where you end up getting an occluded front, where basically the two cool air masses have gotten closer and closer together. They have merged. You end up getting some heavy rain, and then basically the occluded front is when you have this moderate rain with this sort of wedge of warm air that's dipping down between these two semi-merged cold air masses. Thanks a lot for your attention. This has been another SmartFigure.
So now that we've talked about the air masses and frontal boundaries and these mid-latitude cyclones, now we're going to look at the weather, particularly the severe weather that can result from these. And we're going to look at three types: thunderstorms, tornadoes, and hurricanes. So when we talk about cyclones, first of all, know that we're talking about this term cyclone in the true geologic, meteorologic sense. We use the term cyclone to refer to a tornado or a hurricane, but when we use the word cyclone in here, we're using it to refer to a low pressure system. So the vast majority of these cyclones are not hurricanes or tornadoes. They are thunderstorms. So the circulation that's associated with thunderstorms is characterized by up and down movements. When we look at winds in the vicinity of a thunderstorm, they're not typically following that inward pattern, that swirl pattern of a cyclone, typically going to be variable and gusty. Now, thunderstorms can form on their own away from a low pressure system, but they can also form in conjunction with the cyclones. They can be spawned along the cold front, and that's where a lot of times our weather, especially if we look at late summer, we get thunderstorms. And typically what will happen is you'll have a front that's coming, a cold front that's coming, and these thunderstorms will form out in front of that cold front. And they can form, a line of thunderstorms that pushes through. So now we're going to watch a SmartFigure video that looks at the occurrence and development of thunderstorms.
Hello there, this is Callan Bentley. Welcome back for another SmartFigure. After watching this video, you should be able to describe how thunderstorms form. This is a map showing for the 48 contiguous United States the average number of days per year that have thunderstorms. You can see a couple of patterns here. One is that the West Coast has very few thunderstorms per year. Another pattern is that there seems to be a concentration of thunderstorms associated with the Front Range of the Rocky Mountains. And then, of course, there's a very large concentration associated with Florida. So what is responsible for the fact that some areas of our country have more thunderstorms and other areas have fewer? That map correlates closely with the U.S. portion of this map. This is the average annual lightning flashes per square kilometer. So, of course, this is a global map showing where there's a lot of lightning and where there isn't. You'll notice there's a huge concentration over the jungles of equatorial Africa. And then we also have some large concentrations in the interior of South America, basically along the Himalayan front. Indonesia also has a lot of lightning. And then again, you can see that concentration there in Florida and the Gulf Coast states of the United States. So thunderstorms can form in a couple different ways. One is when you have isolated thunderstorms developing within a marine tropical air mass. And this basically is when the land is being heated, the air is rising, and as it rises, it causes condensation to begin to occur, and that condensation, produces precipitation. But as the air is moving up, it basically lofts that precipitation up. And as long as that air is moving up faster than, the size of these little droplets of precipitation, then you don't have any rain. But once the rain becomes too heavy for the air to keep it suspended, it begins to fall. And that's when you end up getting heavy precipitation. And so you end up getting this cumulonimbus cloud that's built up to these towering heights, and updrafts are feeding air in on one side, and then downdrafts are dropping the air and the precipitation out in a very heavy way on another side. You can see there's also some lightning in there as well. And then basically in the final stage of the thunderstorm, the updrafts dissipate, and we basically don't have a source for any new moisture going into the cloud, so the rain tapers off, it's light rain, and eventually the cloud without a new source of moisture will just evaporate, and you'll be left with a fairly nice day. Now there are also thunderstorms that are associated with fronts, and so here's an example of that where you've got a cold front moving into the area. Maybe you could take a look at this picture and think to yourself about what's happening here and what the symptoms would be of the oncoming thunderstorm. Well, hopefully you notice that if you're standing, say, over here on the right side, that's a little stick figure representing you, you might look up and see some cumulus clouds at low levels in the atmosphere and then cirrus clouds up high above. And basically, if you see those cumulus clouds transitioning, basically growing up to higher and higher levels, that indicates that perhaps the cold front is on its way in. Basically here, the cold front is this mass of cold air that's wedging up the warm, high moisture air that you're in. And then basically that builds up the cumulonimbus cloud, and you end up getting your heavy precipitation and your lightning occurring right there at the cold front itself. So this would be more of a regional system of thunderstorms rather than the isolated thunderstorm on a hot day like the example we just looked at. I hope that makes sense to you. Thanks a lot for your attention.
So there you saw a little bit of information about thunderstorm development. So as a bonus question for watching this video, send me an email and indicate how many days per year the state of Arkansas has with thunderstorms, and you'll be awarded some bonus points there. So now if we look at the next type of severe weather that can result, we look at tornadoes. Tornadoes are going to form out of the strongest thunderstorms, typically short duration, but very high in terms of the amount of damage that can result. Tornadoes, of course, sometimes we call these twisters or cyclones. They take the form of a rotating column of air called a vortex. Low pressures inside cause air to continue to rush into the tornado, and that air just kind of rushes in from all directions and continues that spiral or that vortex. Tornadoes are made visible by condensation that is occurring, as well as the debris that's being picked up. And so here, of course, you have a picture of a tornado. So now we're going to watch another SmartFigure video looking at tornado development and climatology associated with tornadoes.
Hi there, it's Callan Bentley. We're back again for another SmartFigure. This time we're going to take a look at mesocyclones and how they relate to tornadoes, and for that matter, how they relate to mid-latitude cyclones. Here is something you probably don't want to see coming towards you. This is a tornado, and it's coming down here in the center of this image, causing very, very high winds on the ground. There's a tremendous pressure gradient associated with tornadoes, and the winds there can approach 480 kilometers per hour. That's 300 miles per hour. So that is really, really fast wind, and it's capable of picking up sheets of sheet metal and hurling them through the air with the force that they could decapitate a person, taking steel girders and jamming them through telephone poles. I mean, it is a really powerful entity. Tornadoes are not evenly distributed over the United States of America. Here's a look at the lower 48 United States, and you can see that tornadoes are definitely more common in certain areas. There's a little cluster in Indiana, another cluster in Florida, but by far most of the tornadoes that we have in the United States of America are located in the Great Plains states in so-called Tornado Alley. And you can see that they are not evenly distributed in time either. The graph over on the left shows that they are more common during the summer than they are at any other time of year. So how do these things form? Well, they're related to mesocyclones, and mesocyclones start off as horizontal cylinders of wind. Basically, as wind is blowing over the land surface, there's more frictional drag at the base, and then there's less frictional drag higher up, so you end up getting these sort of tubes of wind that develop parallel to the ground surface. Now, if it's a hot day, you end up getting updrafts that are also forming at the same time. And those updrafts can take that horizontal cylinder of wind and bring part of it to a higher level in the atmosphere. So this is when the thunderstorm begins to form and you're beginning to form your mesocyclone. The mesocyclone reaches maturity when you end up getting a full-fledged cumulonimbus cloud, and now your cylinder of rotating air is vertical in its orientation. So this is the proper mesocyclone. Note that these things are 3 to 10 kilometers in diameter. Now, at the base of that 3 to 10 kilometer mesocyclone, you may end up seeing tornadoes forming, and so that's where you end up getting the tornadoes. Notice that the tornado is not the same thing as the mesocyclone. The tornado is a much smaller feature. Some tornadoes have multiple suction vortices. So here you're looking at an overall large tornado, but then these suction vortices, here's one suction vortex and here's another, these are on the order of 30 feet across, 10 meters across, something like that. So they're not especially huge, but that's where the highest winds would be located. So the suction vortex is the smallest of the features. Tornadoes are slightly larger, and of course the mesocyclones are slightly larger still. Is there any other rotating column of air that is even larger than a mesocyclone? Well, yeah, as I mentioned in my introduction, there are. Those are these midlatitude cyclones. These are much larger regional features that are hundreds of kilometers across. An example of one of those is over on the right side of this image. And of course, we talked about that in another SmartFigure. Thanks a lot for your attention.
So as you saw there, we get the development of this mesocyclone, and that's due to wind shear. And as that mesocyclone forms, doesn't necessarily mean that tornado formation will follow. Only about half of all mesocyclones produce tornadoes. And as of right now, we don't really have any way to forecast which mesocyclones will spawn tornadoes and which will not. Now, in the video, he showed these suction vortices. If you've ever seen the movie Twister, there's a scene where they're kind of on a bridge or a road kind of surrounded by water, and they're inside the tornado, and you can see those suction vortices kind of swirling around them. It's the scene with the cows where the cows are kind of flying around. But so even though it was fiction, you could really see those individual little suction vortices that can get going within a tornado. And really what that does is it allows more air to be pulled in, really sustaining the tornado for a longer period of time. So tornadoes are capable of generating the strongest winds that we see in nature, and destruction really depends on the wind strength. Tests that have been done in engineering facilities have demonstrated that winds in excess of 200 miles per hour are really capable of incredible feats. And if you look at the bottom of page 593, you see a piece of sheet metal driven into a utility pole. You see a vehicle wrapped around a tree there, and basically the majority of the metal is gone from that vehicle. So the destruction has to do with winds, and we use the enhanced Fujita scale, or the EF scale, to measure the intensity of tornadoes, and this is on page 594. The original scale was developed in 1971. The enhanced Fujita scale was put into use in February 2007, and the wind speeds, of course, are estimates based on damage. We're not really able to measure the exact wind of a tornado. And really what we do is look at the damage. So an EF0 would be light damage. There's some damage to siding, some shingles, you may have some limbs down. Then EF1, a little bit more uprooted trees, bent flagpoles. And then you can see we go up from there. And the strongest tornadoes are EF5 tornadoes. Significant structural deformation. Now, fortunately, we don't have that many EF5 tornadoes. Most tornadoes are EF0 or EF1. In fact, last week, I guess it was, when we had the storms that came through, there were several in the Arklatex. There were, I think they were all rated EF0. Maybe one was an EF1. But fortunately, they were in areas that were not urban and didn't have any structures or anything. So the damage was very, very mild. 63% of tornadoes that occur are EF0 and EF1. 2% are classified as EF4 and EF5, but that 2% of tornadoes accounts for almost 70% of deaths associated with tornadoes. Now, when we look at forecasting tornadoes, of course, they're difficult to forecast because we don't know exactly which mesocyclones are going to produce tornadoes. We have the Storm Prediction Center, which is located in Norman, Oklahoma. It's part of the National Weather Service. And they can issue severe thunderstorm outlooks and basically monitor those. And then they can issue tornado watches or tornado warnings. So a watch is that we need to be on the lookout for the possibility of tornadoes. In other words, conditions are favorable for tornadoes to develop. Tornado watches are issued in broad swaths. So you may see, the entire western side of Arkansas being under a tornado watch. A tornado warning is the serious one. This is issued at a much smaller scale, and this is when the radar has indicated that a tornado has formed, or a storm spotter has actually seen a tornado. So tornado warnings are, hey, it's time to take cover. There is a tornado on the ground headed your way. The other thing that we can do in terms of the tornado warnings is we can estimate a probable path, and that way it alerts the individuals that are in that path, because we pretty much know the direction that tornadoes are going to travel. A lot of the improvements that have been made in tornado forecasting over the years is due to Doppler radar. Doppler radar performs the same tasks as conventional radar, but it also has the ability to detect motion. So it can detect the formation and development of a mesocyclone. And we know that with mesocyclones, the majority of them do produce hail and severe winds. We know about 50% produce tornadoes. Can't really detect the tornado itself, but we can detect the markings of a tornado on radar. Of course, not all tornado-bearing storms have clear-cut signatures on the radar, and other storms can give false signatures, but the use of Doppler radar has really helped to decrease the number of people that have died due to tornadoes over the past 50 years. So our last thing we're going to talk about here are hurricanes. So hurricanes are the most violent storms on Earth. They are intense centers of low pressure that form over tropical oceans. They're characterized by intense thunderstorm activity and strong cyclonic circulation, wind speed in excess of 74 miles per hour. Unlike the mid-latitude cyclones, hurricanes do not have conflicting or contrasting air masses or fronts. The source of the energy that's producing and maintaining that hurricane is the amount of latent heat that is formed. Now, One thing that we do know about hurricanes is that they form between 5 degrees and 20 degrees latitude of the tropical oceans. So now we're going to look at another SmartFigure video about the kind of the profile of a hurricane and where they form.
Hello, this is Callan Bentley. Welcome back for another SmartFigure. After watching this video, you should be able to describe where, when, and how hurricanes form and what the risks are for coastal communities. Hurricanes are the names that we give to storms that are tropical storms that develop a spiral pattern as winds from the surrounding area rush in to a central low pressure zone. And then in the middle, oftentimes there's a well-developed eye region. Tropical storms form both north and south of the equator, but not actually on the equator itself, because you need to have a little bit of the Coriolis effect at work in order to generate this spiral spin of the storm. But it's at the equator where the waters are warmest, and warm waters are, in fact, the fuel that drives hurricanes. So this creates lots of warm, wet air that rises up. That warm, wet air is going to be most common during certain times of the year when it's warmer. And so that's late summer and early fall. That's what we call hurricane season. So there's this rising warm air that generates lots of rain as it rises and cools. Air rushes in, and because of the Coriolis effect, it ends up taking on a curved path, and that produces the overall spiral shape of the storm. Here's an example of a hurricane that's moving towards the land. This is in the region of South and North Carolina. The storm is moving towards the land at 50 kilometers per hour. Now, over on the left side of the storm, the winds are blowing offshore at 175 kilometers per hour. And so the net wind on the left side of the storm is going to be 175 minus 50, or 125 kilometers per hour. On the right side of the storm, the winds are blowing onshore at the same time that the storm system is moving towards the shore. So here you've got a combination of 175 kilometer per hour winds plus 50 kilometer per hour storm movement. And so that adds up to 225 kilometer per hour winds. This is a big deal because it ends up influencing the storm surge, which is the most destructive aspect of these storms. Storm surge is basically a temporary large local rise in sea level that can end up basically damaging low-lying structures. So here you've got a storm that's moving out of the Indian Ocean towards the African coast. This is in the southern hemisphere, which is why you see it spiraling clockwise as opposed to the counterclockwise images we've looked at so far. On the left side of this storm, the winds are blowing onshore. The right side of this storm, they're blowing offshore. Which of the four lettered cities here is going to experience the greatest storm surge? Well, hopefully you said city C, because basically that's the location that's close to the eye of the storm, and the winds are blowing onshore. So basically that's going to be pushing the ocean up onto the land, and plus the low pressure of the storm system is basically going to be pulling the ocean up in that area. So that is going to be the location most at risk of a storm surge. Thanks very much for your attention.
So you got a brief rundown there of kind of how hurricanes form, but just to go into a little bit more detail. So we know that they don't occur right on the equator because we need the Coriolis effect to be able to kind of start this air coming in at an angle. So what happens basically is that you get some clouds, you get a few thunderstorms that are forming over the warm ocean. They're disorganized. There may be a low pressure system, but there's not going to be any or very little rotation. It's going to be very weak. And these are called tropical disturbances. And most of the time, they just die out. But if we're in a situation that's going to favor hurricane development, what happens is latent heat is going to be released from those thunderstorms. And so the areas get warmer. When the areas there get warmer, this lowers the air density, it lowers the surface air pressure. So now we actually have a weak low pressure system, and we start to get the development of a cyclone, basically. As the pressure continues to drop, the pressure gradient increases, so that's going to bring more and more air in, just like we saw with the development of a tornado. But what happens though is since this is forming over the ocean, it's bringing in not just air, but also moisture. And this nurtures the storm growth. The water vapor condenses, that releases heat, so the air starts to rise. And so you kind of get this sinking air in the middle that gets warmed and then rises back up. And then you get outflow. Okay, so this warm air is going to flow outward from the top of the storm. Adiabatic cooling triggers more condensation, the release of more latent heat, a further increase in buoyancy, and so on and so on. And so that's what allows hurricanes to grow. They can start out as a tropical depression with winds 38 miles per hour or below. Tropical storm, 38 to 74 miles per hour, and that's when they're actually named. And then a hurricane or wind speeds greater than 74 miles per hour. Each year, between 80 and 100 tropical storms are going to develop around the world. So hurricanes start to diminish when it moves over ocean waters that can't supply this warm, moist air. It moves over land, or it reaches a condition where air aloft is not favorable. So if we look at destruction, it's going to depend on several factors. Number one, the strength of the storm. What are the winds doing? The size and population density of the area that's affected, and then the shape of the ocean bottom. So what does that continental shelf look like? So we monitor or we measure hurricane intensity on the Saffir-Simpson hurricane scale. And so you can see there hurricane categories 1 through 5. Hurricane category 5s, of course, you see their winds greater than 250 kilometers per hour. A high storm surge, which we're going to talk about in a minute. These are catastrophic hurricanes. So in the video, there was a little bit of mention about storm surge, but storm surge is the most devastating destruction that happens right in the coastal zone. And it's a dome of water that can be 40 to 50 miles wide. And it just basically sweeps across the coast where the eye makes landfall. The storm surge is the height of the water above normal tide level. So if we go back here, we're looking at storm surge. The storm surge associated with hurricane category 5 is greater than 5.4 meters. So we're talking about, higher than 15 feet. So you basically got this ginormous wall of water that just sweeps up on the shore. Excuse me. The worst cases are going to occur in areas like the Gulf of Mexico because the continental shelf is very shallow. And so it basically allows that water to build up higher to be able to push on shore. Bays and rivers can also exacerbate the problem. If it comes in during high tide, that can also make the problem worse. And it's most intense where the winds are blowing toward the shore, as he explained there in the video. Wind damage, of course, is another factor, the most obvious that we can see. Hurricanes also can produce tornadoes. In 2004, there was Tropical Storm Bonnie, and then 5 hurricanes that made landfall: Charlie, Francis, Gaston, Ivan, and Jeannie. Those 6 storms produced nearly 300 tornadoes. So not only do you have to deal with the storm surge and the intense rain and flooding, you may also have to deal with tornadoes as well. Torrential rains can trigger flooding, and most of the time this happens inland. And this is going to depend on, how big the storm is, but also, does it get stalled out? If it comes on shore and it just sits there, then it's going to dump incredible amounts of rain. and in a very short period of time. If it comes on shore and it moves away very quickly and it diminishes very quickly, then the risk for flooding is not as great. So if we look at being able to monitor hurricanes, we have satellites, we have aircraft reconnaissance, we have what they call hurricane hunters that actually fly into the hurricanes and get data, radar from the coast, and also data buoys that are out in the ocean. This has allowed us to really look at the track of a hurricane, and this is called a track forecast. It's difficult to identify accurately, but with the increase in the technology that we've had, current 5-day track forecasts are now as accurate as the 3-day tracks from 20 years ago. So we have gotten a lot more accurate about this. It allows meteorologists to be able to issue hurricane warnings and hurricane watches, and it allows people to be able to take action. So that brings us to the end of chapter 19. We will finish up our study on the atmosphere with chapter 20.